So, welcome to this course on advanced quantum mechanics with applications. In this course, we will learn of course, the basic quantum mechanics and the various applications that have been developing since the last decade or so and various research topics that are associated with it. So, the applications part comes there, but of course, we have to also know the basic quantum mechanics, which I am sure that all of you have studied in your undergraduate or graduate curriculum. So, this is a development on that. I will of course, start with something simple and basic. So, let us look at the historical development of quantum mechanics. So, it gives you a detailed description of the behavior of matter and light, which means photons, and all the phenomena that occur at the subatomic level. So, that is inside the nucleus or inside an atom, whatever phenomena goes on, they are governed by the quantum mechanics and the laws of quantum mechanics. So, Newton initially thought that light consists of particles because it reflects from a mirror, and this gave rise to the corpuscular theory of light. However, towards the beginning of the 20th century, there are lots of experiments done which have manifested the wave character of light, which means that they show interference, diffraction and reflection, etc., which otherwise, especially the interference and the diffraction, they are otherwise absent in the case of particles. So, this gave rise to this famous wave particle duality. So, the conclusion is that light in some experiments show particle character such as photoelectric effect and Compton effect and so on, and in others they show wave character such as interference and diffraction. So, this gave rise to the wave particle duality of matter, and it is not only the priority of photons, other particles, subatomic particles such as electrons and protons, etc., they also show wave particle duality, similar duality as seen for light. So, there is a large amount of information that have started coming in for the atomic systems, and they have raised a lot of curiosity and of course, have given rise to a lot of confusion because of contradicting inferences coming out from various experiments. And well, a lot of people at that time, we are talking about the early 1920s and the mid 1920s, between 1920 and 1930, where a lot of people have contributed to the birth and development of quantum mechanics. Notable among them are Schrodinger, Heisenberg and Born, and they have enriched the field so much so that there are consistent description of matter at very small length scales that have emerged. So, the basic pillars or the basic ideas that they are based upon, mainly two of them. One is called as a probabilistic interpretation. So, this has to be this is distinct from the interpretation or the deterministic interpretation that we are familiar in classical physics. As opposed to that, in quantum mechanics, there is a probabilistic interpretation that needs to be incorporated, which gives rise to a lot of satisfactory answers to a lot of experiments that have been done and phenomena that people have observed. And the second one is the uncertainty principle, which is related to the measurement of a particular measurement, and it sort of saved, these two put together have saved a number of experiments that are done on subatomic particles. So, let us take this brief tour to how things have evolved, and that will make the study of quantum mechanics more interesting, and of course, we will go to the applications part later on. So, let us see some cartoons on a lighter note, so that we understand things in graphics, using graphics. And there are some of them which are, so I have drawn two pillars. The pillars, as I said, are, one is the probabilistic interpretation, the other is the uncertainty principle of quantum mechanics, which was developed by Heisenberg. We'll go through that. And these, say we go through one after another. The probabilistic interpretation was enriched by a simple experiment which is called as a double slit experiment, and it's Young, it's called as a Young's double slit experiment, being performed in 1802, which is more than 200 years ago. So, there are light waves, these vertical lines that you see are really the light waves that are coming, they are approaching these blue barriers, like these ones, these blue barriers. These barriers have two slits, and let us call this as slit 1 here, and this as slit 2 here. So, there are these two slits, and there are these secondary, these act as secondary sources, and when light passes through them and they are allowed to fall on a screen that is kept here. So, this is that screen, and when light falls on this, light undergoes a phase difference from the coming out from the two slits, and this phase difference gives rise to a interference pattern, which means that there are bright bands and dark bands depending on the condition that these path differences or the phase differences that they satisfy, and we get nice bands that are appearing on the screen as is shown below. And these are there in every undergraduate lab, double slit experiment which shows interference patterns due to these two slits. One thing that should be remembered is that the slit width should be comparable to the wavelength of light, which means that if the wavelength of light is of the order of 4000 or 5000 or 6000 angstrom, this should be of the order of a millimeter or so. So, then these, or even less than a millimeter, then these are the well defined interference pattern could be seen. And of course, the interference, the distance between the dark and the bright bands that you see here depends upon the wavelength of light and the slit width, and also the difference between the barrier and the screen that you see here, which I write as D. Now, these are matter of study in optics and in particularly in the interference chapter. Will not elaborate on that. We have brought this for a particular reason of demonstrating how quantum mechanics can be derived, or rather how the probabilistic interpretation can be inferred from this experiment. So, we will skip all the details that what are the conditions for path difference or phase difference to have a constructive or destructive interference and so on, and go on to the quantum mechanical aspects. Now, light is of course, it consists of particles called as photons. So, since we are talking about particles, let us talk about bullets. You see this character which is firing guns through two slits, just like what we have seen in the last slide, and these bullet marks are allowed to fall on a wall which is kept at a distance again, just like the photons were allowed to fall on a screen. Now, the bullets are allowed to impinge on a wall. Now, do you think there will be interference pattern? Certainly not. Okay. So, if these character keeps firing bullets at the wall through the slits, there will be bullet marks that will form along the two slits that are there and on the wall, and there will be no interference pattern, there will be no bright and dark bands that are going to form. So, the question is that if photons are particles, the bullets are particles, why don't bullets give rise to interference pattern, whereas the photons do? Could it happen because the photons come in large numbers, because you are firing a light beam and the light beam has got a very large number of photons. So, is it that because they are coming in large number of photons? So, let us reduce the number. It is a thought experiment, we are not doing that experiment, nobody is firing photons very slowly, they are still at the velocity of light, but it is just a thought experiments. You say that I am going to only release a few photons at a time, and they would go through the two slits as shown here and fall on a screen, and would ultimately give rise to an interference pattern as is seen here. So, if you allow for a long time, then the pattern will build up, and this is important thing. The pattern builds up means that there is interference pattern. So, even if you reduce the number of photons by a large fraction, the phenomena, the basic phenomena that happened earlier do not stop. Okay. So, if they are coming in small numbers, the question is how does the interference pattern take place, or rather it happens. So, how do they interfere? That is the question. So, one solution is of course that the photons interact with themselves. It is not very clear from this statement that we want to say, but they what we mean to say is that they interfere with themselves, or maybe they have a wave character associated with each photon, which we know that certainly that is a possibility. And so, they can interact, coming back to the first point, they can interact within the wavelength of the wave. So, they can actually mutually interfere within the wavelength of a wave, and that could give rise to the pattern. Now, let us reduce the stream even farther and send one photon at a time. Okay. Interference, it is seen that the interference still takes place. Interference, one can still see an interference pattern if you wait for long enough, but there are two slits that are essential. Now, the question is that how does a single photon anticipate the existence of two slits? A photon coming through this slit that is left to mine is the photon that is passing through that slit. When it is passing through this, it of course does not know the existence of the other slit. So, how does the interference still take place if you reduce the stream to such an extent? And the solution is that give up the notion of talking about location of the particle until it hits the screen. So, this picture is this middle picture where we actually see that it is passing through one of the slits is misleading. Do not talk about measuring the position of the particle or the location of the particle until it hits the screen. If it hits the screen, it will leave a mark, and then you know that it has passed through either of the slits. Okay. So, talk about the probabilities of the photons to pass through one slit or the other. So, we do not know, we simply say that the photon must have passed through either the left slit or the right slit, or call it slit 1 and slit 2, but we really do not know. And if you allow that to happen, or allow that or rather you assume that, then the interference pattern can be understood. So, that tells you that the properties of quantum objects are linked to their measurement. So, when you do the measurement, when you talk about the measurement, that is important. So, do not talk about the measurement of the particle when it is passing through one of the slits. You really do not know which slit it is passing through. Similarly, the role of the observer is also crucial. So, if there is an observer to carefully monitor, so suppose there is a robot sitting at one of the slits or at both the slits, and this robot actually knows exactly where it passes through, which slit it passes through. or say there is just one robot which counts the number of photons passing through that slate. So, then immediately you are making it deterministic, and if you do that, then the interference pattern will go away. So, if the observer carefully monitors which slate does the photon go through, will wipe up the interference pattern. So, there is an entangled relationship. This is what we talk about, entanglement in our daily life, that everything is knotted, and so there is a nice entangled relationship between the observer and subatomic objects. This is what one of the basic principles of quantum mechanics. Let us now assess the observer's role. So, this is called as Schrodinger's cat. So, there is a box in which this cat is enclosed, and there is a hammer which is hanging, or rather which is tied to a device or a pulley or some kind of a sort of lever, and this is right over a green colored liquid in a bottle or in a vessel, and this is assumably the poison. So, if you leave the cat inside the room and lock from outside and you do not know what is happening to the cat, either the cat could get very inquisitive or very curious about what is this green colored liquid, and it would sort of disturb this whole apparatus, and this hammer could drop down and break the poison, and if it breaks the poison, then the cat dies. And if the cat dies, then of course, we would open the door and find the cat to be dead. And suppose it could also happen that the cat is in such a strange ambience for the first time, and it does not want to do any mischief with this green colored liquid, and it stays away from it, nothing happens, open the door and you find the cat to be alive. So, let us hope the cat to be alive, but there is always a possibility that cat could be dead because of the reason that we just said. So, once you are out of the room and not watching it, then in your mind there is a 50-50 possibility of the cat to be dead or the cat to be alive, and as soon as you open the door, your the whole state of the room collapses into one of the possible states, say the cat is alive, which is an optimistic scenario. So, it is the observer's role is important. Observer's role only comes when you make an observation or you make a measurement and the system actually collapses into one of its available states. These are called eigenstates of the system. So, the eigenstates of the cat is either it is dead or alive. So, if you want to write it mathematically, then we could write it as it is a 1 by root 2 is a normalization factor, and for the psi of the cat to be alive and it is psi dead. And the moment you made the measurement, it collapses into one of the states. So, the observer's role is very important here. Let us now go to the other pillar that we have talked about of quantum mechanics, that is Heisenberg's uncertainty principle. How we can understand Heisenberg's uncertainty principle simply? This is what a simple sine wave that you see. So, it is a sine x versus x. Okay. So, this is your y axis in which you plot sine x, and this x axis you plot x. So, it is a one sine wave. These are two sine waves. So, the top panel shows two sine waves with frequencies f1 and f2 with a green and red line, and below that is a superposition of these two sine waves, namely which consists of f1 and f2. And what happens when we superpose many sine waves? You see, by superposing two sine waves, it is getting shrunk on the these period, that is the periodicity is getting shrunk, and so these two are at the same phase. And of course, we are getting that this that the particle is getting localized, and if you superpose many such sine waves, it will be absolutely localized, and we will see what is seen here, which is like a delta function. So, if you take many sine waves, sine k 1 x plus sine k 2 x plus sine k 3 x plus sine k 4 x and so on, and then try to plot them where k is equal to 2 pi over lambda, and lambda is related to the frequencies and so on. So, these are will give rise to a delta function type structure, where the particle is if the particle is associated with this sign with this wave packet, which we called as wave packet, where we superpose many sine waves, these will look like this. So, what it means is that this is the essence of uncertainty principle, that if you try to localize a particle, if you try to do a precise measurement of its position, you have to give up upon the momentum uncertainties, as here the momentum uncertainty is really infinity, because a very large number of sine waves have been superposed, and they are over a range, over a spectrum. So, that the delta p is very large at the expense of delta x to be very small. So, the relationship is that the delta p and delta x, this should be order of h cross, or h, we will see in just a short while that what h means, or this is h cross is equal to h over 2 pi, where h is known as the Planck's constant. So, this is the essence of the uncertainty principle. I will show an interesting picture. This is written there that superpose many sine waves and the wave becomes more localized, and this localization leads to a very large uncertainty in the momentum. So, particle is localized at the cost of huge uncertainty in the value of the momentum, and this is what the statement of the uncertainty principle is. So, this is a famous joke which was so apparently these are two cars. So, there is a police car which is chasing this black car. The police car is in red and white, and apparently this is being driven by Heisenberg, and the police apprehends him for speeding, and when he is caught speeding, he says that the police asks him that, do you know how fast are you driving, because you have broken all the speed limits. Heisenberg says, no, but I know exactly where I am. So, this he says my delta x is equal to 0. However, since I do not know how fast I was driving, so my delta v or my delta p is unknown to me, or it is large, but I know exactly where I am, means my delta x is very small, which means that my position uncertainty is very small. This is just a cartoon, or just on a lighter note what it is, what is the essence of uncertainty principle. Now, let us ask a very pertinent question. So, we are talking about quantum mechanics right from the beginning, it is applicable to whom? And the answer is that to everything in the universe. And so, for majority of the things that we see around are really the limiting cases of the quantum world that we live in. Okay. So, we will see that how, so what is the meaning of then studying classical physics at all levels? I mean, in the sense starting from your school level, and then to your undergraduate level, and then your graduate level, and so on, that classical mechanics, classical physics, classical electrodynamics that we talk about, then what is the existence of that, or rather what is the utility of that, and that will show that these are the classical world is really a limit of the quantum world. Quantum mechanics, as said earlier a number of times, that it is applicable to subatomic particles, and the most familiar subatomic particles are fermions and bosons. and we do not want to get into details about their properties, but just for your information, they are the fermions obey Fermi-Dirac statistics. They have antisymmetric wave function, they have half integer spins, the occupation is restricted, and basically they obey Pauli exclusion principle, and then they are indistinguishable, and the examples are electron, proton, neutron, quarks, etc. Whereas bosons obey Bose-Einstein statistics, they have symmetric function, they are integer spins, there is no restriction on occupation of bosons in a given energy state or given quantum level. They are of course also indistinguishable just like the fermions, and the examples are photons, phonons, pi mesons, etc. So, just another cartoon of showing that bosons can actually be in any of the states. Here is shown as a ground state. That phenomena has a particular name which is called as Bose-Einstein condensation, whereas the fermions, two fermions cannot occupy the same level. So, they are distributed over all these excited state energy levels as well, or rather all the energy levels that appear here. So, how the quantum mechanics was thought to be invented, or people have started talking about it. How did that happen? So, it happened with a simple experiment which is called as a black body radiation. Now, again I will not go into what was the definition of a black body, but a black body is a body which absorbs all the radiation that incidents on it. So, we are talking about the radiation from the sun and radiation from other stellar bodies. So, suppose you have a body which absorbs all the radiation and emits nothing, then that is called as a perfect black body. So, such black bodies, one was interested in seeing that how the intensity of the spectra emitted. So, we are talking about also emission spectra. So, it emits some radiation, so does not absorb everything. So, the emission spectra and as a function of frequency and at a given temperature. Okay. And what was shown is that it shows a nice, I will use another color to give a guide to your eye. So, this is that experimentally it is found that it has a non-monotonic dependence, whereas the classical theory predicts that it should go like this. And then there was another theory that was made by Rayleigh and Jeans, which says that it goes like this. So, nobody actually predicted that it goes up and then goes down, and this was a problem at hand with Planck. And Planck almost like, as he explained later, that as a matter of desperation, he had proposed something which we will just see in a while. And so, this is called as the ultraviolet catastrophe, that this classical kinetic theory predicts energy radiated to increase the square of the frequency and so on. So, these are all wrong, and what you see, these non-monotonic thing or these thing here that you see here are the ones that are correct and experimentally observable, and this is shown as a function of frequency, this is shown as a function of wavelength. However, they all carry similar meaning, or rather it just says that at a given temperature, if you look at the intensity of the radiation, then either as a function of frequency or wavelength, one sees a non-monotonic nature which cannot be explained by classical theory. So, Planck's solution was that it said that, look, he made a bold assumption that light is emitted or absorbed in some discrete packets or quantum which is given by E equal to h nu, where nu is the frequency of the light, and this h is called as the Planck's constant. We will just detail these little later, and this h has a value which is 6.627 into 10 to the power minus 27 erg second, or equivalently it's 6.6 into 10 to the power minus 34 joules second, and so on. So, E equal to h nu. So, energy of this emitted radiation is not a continuous stream. This happens in packets, and each packet has an energy which is h nu. Nu is the spectral frequency, and h is of course here looks like a constant of proportionality, that is what we will call, but it is known as Planck's constant. Planck initially called this theory as an act of desperation. He says that I knew that the problem is of fundamental significance for physics. I knew the formula that reproduces the energy distribution in normal spectrum. A theoretical interpretation had to be found no matter how high. So, it leads to the consequence that light comes only in certain packets or quanta. This is a complete breakdown on classical physics, or where all the physical quantities are known to be always continuous. The Indian scientist S. N. Bose had a large contribution here. What Planck did on an ad hoc basis, he actually wrote down the correct distribution for the photons, which is known as the Bose-Einstein distribution. So, there are more advances into this subject of quantum theory. It is required to look at this origin of these quantity called h. It is also called as a quantum of action. It is popularly of course known as Planck's constant, and it is, as I told, that it can be thought of as a proportionality constant of this equation, where gamma is the spectral frequency. So, let us see that when is these h important. So, let us take an example. So, consider a macroscopic oscillator a classical oscillator, that is, of mass 0.01 kg, and the maximum velocity of the oscillator is equal to 0.1 meter per second, and the amplitude, and so basically the amplitude of oscillation is amplitude equal to 0.01 meter. Now, of course, we know that this does not fall into the realm of quantum physics, but we will show that explicitly. So, what is the solution of a classical oscillator? It is x equal to a sine omega t, a sine or cosine does not matter, which gives you a dx dt equal to a omega cos omega t, which tells you that it is equal to a omega into 1 minus x by a whole square, which is equal to omega into a square minus x square. So, that is the velocity of the oscillator. The maximum velocity of the oscillator is when x equal to 0, that is when the oscillator is at the mean position, and so dx dt max which is equal to V max happens when x equal to 0, which is the same as the mean position, and this is equal to omega into root over. So, we will just put this equal to 0, and this becomes equal to a omega. So, at x equal to 0, it is equal to a omega, which is equal to a 2 pi a nu, where nu is equal to V max divided by 2 pi into amplitude. So, if you do this 0.1, 2 pi is 6.28 into 0.01, which is the amplitude, this comes out to be 1.6 hertz. So, that is the frequency of oscillation of this thing, and the time that is associated with these frequency, which is equal to say t equal to 1 over nu, which is 1 divided by 1.6, which is equal to approximately 0.63 second. Okay. So, what is the energy associated with this oscillator? Energy E. We are talking about the total energy, which is of course the kinetic energy, but at the potential energy. But when it is at the mean position, this is what the total energy is. If you put in all these values of m, etc., and V max that we have written earlier, it comes out as 5.5 into 10 to the power minus 5 joules. So, this energy E into T, which is so the product of the E and T, that is 10 to the power of the order of 10 to the power minus 5 or 10 to the power minus whatever 4 or something. So, this E t is certainly much greater than h. So, these canonical variables such as energy and time, they are, when they are multiplied, they give values which are much greater than h, because h is of the order of 10 to the power minus 34 joule second, and this is only coming out to be 10 to the power minus 4 or 10 to the power minus 5. So, the conclusion is that the quantum effects are negligible. So, these quantum effects are negligible, and so we are in the classical regime, and we can safely employ formula of classical physics. So, that is the importance of H that we want to bring out. Now, Bohr realized that this wave particle duality, not particles, wave particle duality is not the monopoly of photons, it is applicable to massive particles as well. What we mean by massive is that which has a mass, it necessarily does not need to be heavy. Such as electrons, they show interference, diffraction, and a variety of other phenomena which are applicable to waves. Thus, there is a general question, if the particle has a wave description and wave has a corpuscular description, means particle description, how are the properties interlinked? And de Broglie solved this problem. He said that, look, the momentum of the particle is related to the wavelength of the wave. So, a single thing or a single particle or a single object can have both the descriptions, both particle and wave description. The wavelength of the wave is related to the momentum of the particle, and this is by this relation p equal to h over lambda. This is called as de Broglie relationship. So, if h is 0, no matter what the momentum of the particle is, the wavelength associated with the wave should identically be equal to 0, and we should be in the classical regime, as we have just seen in the example or the illustration just in the last slide or the earlier slide.